right, everyone, it is the top of the hour, so we're going to go ahead and get started here today. Thanks for joining us for another session in our U.S. Territories Water Operator Training Series. This is going to be session 4, and we're going to be doing applied water math, looking at area, volume, and pressure. This is going to be a math webinar that's going to build on what we learned a couple of weeks ago during our basic water math course, and I recommend going back and watching the recordings of some of these webinars, especially the math. We have to go really fast because we're covering a lot of things today. But you all will have access to the recording of this, so you can go back over things if you need to. We're just gonna jump right in today, and thanks for joining us. So I'm Shannon Pepper. I am a water utility trainer and specialist at the Southwest Environmental Finance Center. My email's on the screen here, and please feel free to reach out to me if you have any questions following today's presentation. My doors are open. I'm happy to answer questions after the fact if you have any clarification that you'd like. So the Southwest Environmental Finance Center, as you all hopefully know, is part of the UNM, the University of New Mexico School of Engineering. This training series is also funded by support from the US EPA. Just a little quick note about meeting controls. There's a black bar either at the bottom or the side of your screen that has all these little buttons on it. Pay special attention to the audio and the video buttons. So the audio will mute, unmute, the video will start and stop your video. For mute and unmute, that's going to be especially important for those of you who are in a classroom. It may be easier to just be on unmute the whole time. But if most of us could kind of keep the mute unless we're asking a question, and then please feel free to hit that unmute so that I can hear you. But we want to try to control the background noise as much as possible. Also, please utilize the chat. That's that little box with the 3 dots in it. If you have any questions as we go along today, the chat is a really great place to do that. Andrew and Valeria are both kind of keeping an eye on the chats. Also, it looks like Andrew has sent you the link to the previous trainings and the recordings. Thanks for doing that, Andrew. And that's in the chat this morning as well. Okay. So this training series is meant to cover the basic need-to-know criteria for the WPI ABC operator certification exams. We're covering the basic need-to-know criteria for operator classes 1 and 2. We might go into a little bit of 3 and 4 details as well, but mostly focusing on covering 1 and 2 for this series. Here's our schedule for 2025. So as I said, we're on session 4, and then there's a bunch more after this. These are bi-weekly, always on the same day. So make sure that you've got these on your calendar if you're planning on attending the whole series. And this is that website that Andrew put in the chat for us. This has our training schedule for the wastewater series, and as well as previous recordings. So this is a really helpful one to have in your bookmarks. Please make sure that you sign in during every session to make sure that you get credit for attending. There should be a facilitator at your location with a sign-in sheet. Make sure that you fill that out so that you can get your credits. Okay, so we're just going to dive right in here. Let's talk about surface area. So surface area is, when we're talking about surface area, we're talking about 2-dimensional space. So flat plane, right? And the units that you're going to see that will usually indicate to you that you're dealing with surface area, you'll see inches squared, and that little squared, we'll get into this a little bit more, but that basically refers to this kind of flat plane, this 2-dimensional space. So we're going to look at feet squared. You might see miles squared, meters squared, and acre. So those are the kinds of spatial units that we'll be talking about with surface area. And luckily, you can usually convert between these different units because they're all measuring the same thing, which is flat 2-dimensional space. And so there are conversion factors that we can use for that. So just maybe think about to yourself, where in a water system do you think our surface area is important? Where would these kind of come into play? So here's a few examples. There's a lot more. But one example, might be a pond liner. It might be if you're calculating how much weed fabric you need to cover a space, maybe around one of your tanks or within an enclosure. You might be looking at how much paint you need to buy for one of your tanks. Or pipes. You might be looking at building materials, siding for a building, flooring, these kinds of things. And here are some more kind of direct examples with some photo examples. Copper sulfate application for algae control in one of your ponds, potentially in pounds per acre. Um, we might be looking at filter backwash rise rates. And this is a formula here that is in your formula chart, your formula table that will be available to you when you're taking your exam. And if you don't have access to this formula table, I can drop it in the chat at the end of the presentation to make sure that you all have it going forward. You might also be needing surface area to calculate surface loading rates or surface overflow rates. Again, this is an equation that is in your formula sheet, and we'll be referencing that throughout the webinar today. Some more examples. So these are directly from your formula sheet. Area of a circle, area of a cone, cylinder, rectangle, triangle, a little less common, but still sometimes comes in. Today, we're going to focus on area of a circle and area of a rectangle, because those are the ones that are probably going to come up the most often. But you might need to calculate cones and cylinders at some point as well. So having these equations on hand is important. So let's look at a surface area example. We're going to start with a square or a rectangle. So say you need to buy some new liner for your reverse osmosis reject water pond, perhaps we could say a lagoon, since y'all are wastewater. Oh no, you all are water folks, so this is good. The pond is 64 feet long and 32 feet wide. How many square feet do you need to order for this pond? So for this question, we're looking at area of a rectangle. That's going to be the equation that we're working with. And to find the area of a rectangle, all we're doing is taking the length of that area and multiplying it by the width. So the length is always the long side of that rectangle, and the width is going to be the short side of that rectangle. So in this problem, the length is 64 feet and the width is 32 feet. So the equation that we're going to be working with, length times width, we're just going to take that long side, 64 feet, plug it into that equation, take that short side, that 32 feet, plug that into the equation. And so our equation now is area is going to be 64 feet times 32 feet. And so we're going to multiply 64 times 32. If you put that in your calculator, you'll get 2,048. And then we're also, take note here that we're multiplying these units. So anytime you're working with a unit and you have it in the equation, you got to keep that unit, because that unit does mean something. It doesn't just get tagged on the end. It's part of your equation. So when you multiply feet times feet, you're going to get feet squared, or feet to the second power. That's an exponent. And that's going to also, you're going to see that come up again and again in your area problem. So keep track of those units as you do these problems. Let's also go over an example for surface area of a circle. What's the surface area in square feet of a circular sedimentation basin that's 60 feet in diameter? Okay, so when we're talking about circles, we're usually using a couple of different points of measure where we might be using diameter. We could also use radius, and we have these two different equations that are available to us. If you would rather work with the diameter, you can use that equation on the top. If you want to work with radius, you can use that equation on the bottom. The radius is just half the diameter, so keep that in mind. Diameter is the length across the circle, and then the radius is just going to be half that length. So if we wanted to, I feel most comfortable personally using the 3.14 times radius squared, because I just remember it's in my head from school. 3.14 is pi. So I would say pi r squared, pi times the radius squared is going to give us that area of that circle. So we're going to work with that equation for this one. You could also use the top one if you wanted to. So if we use that base equation, we're going to plug our radius in, right? So if we got that diameter is 60 feet, we know that the radius is 30 feet because that's half of 60. So we're going to take that 30 feet, we're going to plug it into that equation. We have 3.14 or pi times 30 feet squared. And if we do 30 feet squared, that's going to be 30 times 30 is going to be 900. So we've got 900 feet squared times 3.14 as our final calculation. And our final answer will be an area of 2,826 feet squared for a circle with a diameter of 60 feet. So does that all make sense? If I'm going too fast, put a question in the chat. I'd be happy to go back over anything as we go along here. But I would like to also just throw a practice problem at you. If you've got any questions during this practice problem, feel free to either speak up and unmute, or you can put the question in the chat. Attendee from our last class last week asked that we do these questions as polls, and I thought that was a really good idea. So I'm going to give you this question now, and then I'm going to give you a few minutes to work through it, and then I'm going to have Valeria throw up a poll, and you'll put your answer into the poll, and then you'll be able to kind of check and see how you did. So how many square feet of weed cloth will you have to order to cover the fenced area around your 25-foot diameter tank? And the fenced area is going to be 90 feet by 90 feet. Okay. So we're working with two different area calculations here, right? Go ahead and give it your best shot. I'm going to give you 3 minutes to work on this, and then I'll have Valeria throw up the poll, and then we'll be able to check your answers, and we'll go through the whole thing together. Also, I hope everyone has a calculator and a pen of some kind, either it's your phone or a handheld calculator or a pencil or a pen and paper. Being able to write these things out is really, really helpful. I can't do these calculations in my head, so do write it out. And I'll give you a couple minutes here to work on that. All right, so Valeria, would you go ahead and throw the poll up? And everyone, would you please go ahead and put in whatever answer you got for this one in the poll. Also, just so you know, you might notice that the poll has this weird feet with like a little caret and a 2. That just means that's the same as writing feet squared. It's just that the Zoom polls don't really recognize those special exponent characters. So that's another way to write that, but it means the same thing. Okay. A bunch of people still haven't put in responses, but I'm gonna give you another 20 seconds. Put a response in there, and then I'll close the poll and we can check our results. Okay, I'm gonna close the poll. Let's see how we did here. Okay, so some of you said B, 7,610, and a couple of you also said C, 8,100. So let's go ahead and walk through that together and see what we get. So for this one, we're working with two different area calculations, right? And then there's also a kind of tricky part. So we're going to break down this question. We're looking at how many square feet. So when you see that in a question, usually that means you're like, okay, I'm going to be working with surface area. And then we've got a 25-foot diameter tank in the middle of a 90-foot by 90-foot fenced area. So we have a larger space, but since we're using weed cloth to cover this, we don't need weed cloth to cover the tank, right? So we just need to find the area that will cover around the tank. So how might we do that? We're going to first calculate the length times the width. So we're going to get the area of the full rectangle, or the square, I guess it is, of that whole space. So length times width But we don't want to have that tank in the middle, so we're going to subtract whatever area we get for the area of the tank. And we're kind of even though a tank is a cylinder in this problem, we're thinking about it as a circle really, because we're kind of looking at it from above. And all we care about is that space that's cut out by the bottom of the tank so that we don't have to put wheat cloth there, right? So we're going to subtract the area of the tank from the area of the whole fenced area, and that's going to give us how much wheat cloth we need to cover that space. So length times width, if we kind of plug this in with all these numbers, we're using radius. We're going to get 90 feet by times 90 feet. So that's the first part, minus 3.14 pi times the radius, 12.5 feet squared. And remember our PEMDAS, our order of operations from basic math that we went over a couple weeks ago, parentheses first, then exponents, multiplication, division, addition, subtraction. So in this equation that we're looking at here, we're going to do those parentheses first. So we're going to go 12.5 feet squared, and that's going to give us 12.5 times 12.5 is 156.25. And then those feet get squared. So we add that. Then we also have this multiplication on the other side of the equation, or on the early in the equation, 90 times 90, that's going to be 8,100. Because those are each individual feet and they're multiplying together, that's going to give us feet squared. So now all we have to do is multiply that 3.14 times 156.25. And that finally gives us 8,100 feet squared minus 490 feet squared. And that's a grand total of 7,610 feet squared. Hopefully that made sense, that explanation. If you've got any questions about that, please shoot it in the chat and I'm happy to go over it again. But that's going to be that basic thing. Kind of had to put those two, smush those two together for this problem. Okay. So that's two-dimensional space. Let's talk a little bit about three-dimensional space for our water math. So when we're talking, we just talked about rectangles and circles, three-dimensional versions of those shapes. One example of that is going to be the volume of a box. So when we talk about surface area, we're using the word area. When we talk about three dimensions, three different dimensions of space, length, width, and height, then that's going to be volume. So if we're trying to find the volume of a box, we calculate, first it's going to seem similar, right? The area, which is length times width, but then we're adding that third dimension of the space, which is height as well. And that's what makes it a calculation for volume of a box. So in this example, here we've got what is the volume in gallons of a rectangular tank with dimensions of 30 feet in length, 10 feet wide, and 50 feet in height. So our equation that we're working with, volume of a box equals length times width times height. So we're going to plug 30 feet, which is the length, times the width, which is 10 feet, times the height, which is 15 feet. So our equation for that one is 30 times 10 times 15, and then all those feet units get, singular feet units get multiplied together, which gives us a final answer of 4,500 feet cubed. So again, make sure you're tracking those units. Here the units are feet. They're singular to begin with because you're just measuring one length of a side. But then when they get multiplied together in this equation, then we end up needing to have those in feet cubed. And that's how we end up with cubic feet as a unit to measure volume. We also, in this problem, remember that this problem is asking for volume in gallons. So we have another calculation that we need to do. We're going to do a unit conversion here. So this is a unit conversion. This is available on your formula sheet. The conversion we know is what there in 1 cubic feet of water, there are 7.48 gallons. So that's going to be our unit conversion. So remember that to do this, we're going to take our original number, so our volume calculation in feet cubed, and we want to get it in gallons. So we're going to multiply that starting number by our conversion unit. So We've got 7.48 gallons over 1 cubic foot. Per 1 cubic foot is another way of saying that. In this equation, we can also go ahead and I like to think about conversions in a grid. This might look familiar from last time. I find this a lot easier to calculate, makes more sense to me. So if we put it in a grid, we start with that volume, 4,500 feet cubed over 1, because that it's anything divided by 1 is just itself. So that's 1. And then we have on our other side of the grid 7.48 gallons for 1 cubic foot of water. And what we can do in this grid is we see that there's feet cubed on the top, feet cubed on the bottom. Those cancel out because we're dividing by the cubic feet by another cubic foot unit. So those cancel out. Now we have just ones on the bottom, which is great. And we just multiply across the top of this grid, 4,500 times 7.48. And we're left with this nice gallons unit, and that's what we want our answer in. So 4,500 times 7.48 is going to give us 33,660 gallons. But wait, in this answer, do we need to know our volume that accurately? So in this problem, we have significant figures here. You might notice that we have significant figures of 30. We have, two significant figures in our question, 30, 10, 15. In our conversion, we've got 3. But we're kind of, when we look at significant figures, this is kind of important for, paying attention in the exam to what kind of, how kind of accurate your numerical response should be. And it'll change your calculations if you're rounding up or down within each question. So pay attention to your significant units or significant numbers. In this response or this answer, our original answer, right, was 33,660. That's a little more like of a precise number than we need based on how many significant figures are in the question. So we're going to round up, right? Because 600, looking at 33,660, we want to go to 2 significant figures, and 660 is closer to 34,000 than it is to 33,000. So we're going to be rounding up for this one. And that's going to give us an answer of 34,000 gallons. Okay, that's a little bit of a review from a concept we went over last time. Let me know if you have any questions on that. Okay. So for a question that I'll have you all work on by yourselves or with the people in your room, let's look at an example. So in part 1 of this question, we're digging a trench to put in a new section of pipe. That trench is going to be 4 feet deep, 2 feet wide, and 200 feet long. How many cubic feet of dirt did we excavate? So keep in mind our area calculation for a rectangular box. And that's what you're going to be using for this question. So I'm going to give you all 2 minutes to work on this, and then we'll have Valeria put the poll up, and you all can submit your answers, and then we'll move on to the next part of this question. Okay. Valeria, will you go ahead and put the poll up for this one? So everyone go ahead and put in whatever answer you got for this first part of this question. Awesome, thanks. Great. Okay, I'm going to leave that up for about 10 more seconds for the chance to get in your responses. All right, and I'm going to go ahead and end that poll. Let's see what we got for a result. So everyone who answered 1,600 feet cubed. Great job. Okay, so for this one, right, we're just working with a volume calculation for a box. And that equation is going to be volume of that box equals length times width times height. Pretty straightforward. They gave us that in the question. We know that we have a length of 200 feet, width of 2 feet, and a depth of 4 feet. So we just multiply all those together, and we get 200 times 2 times 4 is going to be 1600. And then this was a little bit tricky, right? Because we also had a decoy answer of 1600 feet squared. But because we're multiplying these feet together, each individual foot unit, foot times foot times foot is going to give us feet cubed. And we know we're working with volume, so cubic feet is what we want in our final answer. So great job on that one. Okay, so this is part 2 of this question. We need to now backfill in our 1,600 cubic foot hole. And then you need to order fill dirt that's sold by the truckload. So how many truckloads of dirt do you need if one truck holds 10 cubic yards, right? Because most people will measure, at least in my experience, will measure truckloads in cubic yards, not cubic feet. So we'll need to do this conversion to figure out how much fill dirt we need to order. And so this is going to be a conversion problem. We know that 1 yard equals 3 feet. 1 cubic yard is 27 cubic feet. Okay, so I'm going to give you all 2 minutes to work on this part of the question, and then I'll throw the poll up and we'll see how you did. Okay, I'm going to go ahead and close the poll here. And show those results. Okay, so we got some mixed results on this one. Let's see how we calculate this. So we're trying to fill in our 1,600 cubic foot hole. We need to know how many truckloads we need to do that if one truck holds 10 cubic yards. So first thing we got to do is figure out how much fill dirt we will need in cubic yards. So we're starting with cubic feet. We need that number in cubic yards. Okay, so the conversion, as we know, we can work either with this kind of like base conversion or this slightly shortcutty version. But if we're doing a conversion, let's just kind of walk through how we would do that for this basic conversion, 1,600 cubic feet. So for this conversion, we're multiplying by this conversion factor of 1 yard per every 3 feet. And because we need this in cubic yards, we're gonna do this we're gonna kind of use this conversion factor and multiply it 3 times across. So if we do that, put that into our grid format here, right? Cubic feet is just feet times feet times feet, right? So you can kind of break this down. We've got 3 feet, 3 different feet units on the top, 3 feet units on the bottom. Those can all cancel out. And we also are able to, if we multiply across the top of this equation, we're going to have cubic yards left over because we have yard times yard times yard. But then also we're going to be dividing by these 3 feet multiplied by each other across the bottom. So feet cancel out. We're left with 1,600 divided by 3 times 3 times 3. And that's going to give us an answer of 59 cubic yards for our volume. Okay. Another way we can look at this is in cubic yards. As I said, this is kind of a shortcut version. It's like a little more simple, I think, to understand. We need to convert this to truckloads because, right, each truck holds 10 cubic yards. So we're going to take that answer that we got in the first part. We're going to plug it into our grid method for finding this conversion. So we have 59 yards to the third on the top, and over 1. And then we're going to, on the other side of the grid, have 1 truckload for 10 cubic yards. Those cubic yards are going to cancel each other out. And we're left with just truckloads. And since we have a top and a bottom number, we're going to go 59 times 1 is just 59. 59 divided by 10 times 1 will be 59 divided by 10, which gives us a final answer of 6 truckloads of fill dirt. Okay, that one was a little complex. There's a couple different parts that you needed to break it down into. Good job, good effort. Okay, so let's look at volume of a cylinder next. So a cylinder, you can kind of think of a cylinder as like a bunch of circles all stacked on top of each other. Um, so really we're working first with that. Remember that calculation for a circle is going to be, you have two different options. You can either do pi or 3.14 times the radius squared, or you can do 0.785 times the diameter squared. And either one will give you the same answer for area. But then because we're working with volume, we have this added dimension of height. So we also will multiply that by height in both cases, no matter which one we go with. Um, oh, and also, yeah, remember that the radius is going to be half the diameter, right? So here in this little photo, you can see the radius is still just half the diameter of the circular part of that cylinder. And yeah, the diameter, or d as we'll shorthand it, is equal to the radius times 2, or 1/2 the diameter. So let's take a look at an example. How would we calculate the volume of a cylinder with that equation? So you're trying to figure out how much water is in your water system at any given time. You have one storage tank with a diameter of 10 feet and is 16 feet tall, and 44,000 feet of water lines that are 8 inches in diameter. What is the volume of water in the full tank and the lines? So we've got two different cylinder area or cylinder volume calculations to do for this one, right? First, let's go ahead and find the volume of the tank. So we're going to take this base equation of pi, or 3.14, times the radius squared times the height of our cylinder. So if we plug in what we know from our question, that storage tank has a diameter of 10 feet, right? And it's 16 feet tall. So if we're using this pi version of the equation, we need to find the radius. We're given the diameter, so we need to go 10 divided by 2, because the radius is 1/2 the diameter, squared times 16 feet of the height. And now we're just using our order of operations here. We're going to do what's inside the parentheses first. So we'll do 10 feet divided by 2 squared is going to give us 5 feet squared times 3.14 times 16.
Have a great Thursday. You too, thank you.
25 feet squared times 3.14 times 16 feet. So that's going to give us a volume of 78.5 feet squared times 16 feet. And if we multiply those by each other, paying attention to our units, that gives us a final answer of 1,260 feet cubed. Okay, so that's the volume of the cylinder, of the tank. Now let's calculate the volume in the pipes next, because we need to find that total volume for the whole system. So first we're going to convert inches into feet. So we know that the water lines are 8 feet in diameter. Because we're calculating the total volume in cubic feet, we're going to need to convert those inches in diameter to feet. So we know that we have a conversion factor, right? And that conversion factor is going to be for every 1 foot, we have 12 inches. So we can take that diameter of the pipe, 8 inches, do our conversion, multiply it by 1 foot over 12 inches. Those inches units cancel out because there's one on the top and one on the bottom. We divide 8 by 12. We're left with feet units, and that's going to be 8 divided by 12 is 0.67. So now we can take that number, that diameter, and put it into our volume equation for the pipe. It's going to be the same as the one before. So 3.14 times the radius squared times the length. And we know that the length is 4,000. And then to find the radius, right, because this is the diameter, we're going to just need to divide that number by 2. So 0.67 feet divided by 2, and then squared. And then we'll do what's inside the parentheses first. That's going to give us 0.33 feet squared inside. And then we can go ahead and just square. When you square a decimal, by the way, you're going to get a smaller answer on the other side. So 0.33 times 0.33 is actually going to give us 0.11. So we're getting smaller. And then since we have those feet units, those get squared. And now what we have to do is multiply across here. 3.14 times 0.11 feet squared will give us 0.35 feet squared times 4,000 feet, because we're going feet squared times feet. That's going to give us feet cubed in our final answer, and the 0.35 times 4,000 will be 1,400 feet cubed. Okay, and now to find the volume in the entire system, we just need to add those two together, right? We're just trying to find the whole volume. So 1,260 cubic feet plus 1,400 cubic feet is going to give us a final answer of 2,660 cubic feet. And we're paying attention to our significant figures, right? So if we're doing that and tracking our significant figures in our answer, let's round up to 2,700 cubic feet total volume in our system. Okay. So now we've seen that example. I'll let you all have a go at it. So in this problem, you have a tank that is 42 feet in diameter and has 56 feet of water in it. So we're talking about a height of 56 feet. How many gallons of water are in this tank? So here are some equations that you have to work with. We have volume of cylinder, two different options, and also a conversion for cubic feet to gallons. So go ahead and take those equations, give it a try. I'll give you, let's see, 2 minutes to work on this, and then I'll put up the poll and we'll see how we did. Okay. Let me go ahead and close the poll here. Let's see how we did. Okay, so we had kind of mixed answers on this one too. So let's go ahead and walk through it together and see how we get to the final answer here. So for this one, we're looking at doing a volume calculation, right? We're calculating the volume of this cylinder. So for the volume of a cylinder, we're working with an equation. I'm going to use pi r squared times the height for this one. So that's going to be 3.14. And then since we have a diameter of 42 feet, that means that our radius is going to be half that, which 42 divided by 2 equals 21. So that's going to be our radius. So put that in for radius. And then we have a height of 56 feet. Okay, so now we just work across this equation. 21 feet squared is going to give us 21 times 21 is 441. We get feet squared. And then we'll just multiply across here. 3.14 times 441 feet squared times 56 feet gives us 77,545 cubic feet. But remember that in this question, they're asking for gallons of water, not cubic feet of water. So we're going to need to do a conversion from cubic feet to gallons. To do that, we're going to set up our grid. And we're starting with 77,545 cubic feet. We put that over 1 for our left side of the grid. For our right side of the grid, we have our conversion factor of 7.48 gallons for every cubic foot. We've got a cubic foot on the top and the bottom, so we get to cancel those units out. And that leaves us just with gallons. And all we have to do is multiply across the top of this grid. There's just ones on the bottom, so we don't have to do any dividing. 77,545 times 7.48 gives us 580,000 gallons is our final answer here. Okay. So if you have any questions on that, after that explanation, please feel free to drop them in the chat. I'm also going to just move on to a kind of slightly different topic here. We're just going to look briefly at water pressure. Water pressure is something that we have to think about as operators. We want to understand how elevation changes affect pressure in your system, understand how water loss control can be optimized through your good pressure management. And also understanding and controlling tank levels in order to meet pressure goals for your distribution system. Um, when we talk about pressure and feet of head, this is kind of an interesting one. So if we have two different kinds of tanks here, we've got a really wide tank with a really skinny tank. They're the same height. Say tank A is 5 feet in diameter and 75 feet tall. Tank B is 50 feet in diameter, 75 feet tall, and holds 1.1 million gallons of water. So here's a question for all of you. If you want to toss an answer in the chat or just shout it out. If each tank has a pressure gauge right there at the bottom of it, which tank do you think has the highest pressure? Which tank will read the highest pressure at that pressure gauge at the bottom? What do you think? Okay, hearing only, oh, somebody put an answer, let's see. Same. Yeah, exactly. You're spot on, Melissa. So it's going to be the same pressure, right? Because we measure pressure by the height of the water, not by the volume. So you might think, it might be kind of tricky. You might think that tank B holds, it has a higher pressure reading, but they're actually the same because they're the same height. And so with pressure, we're thinking about the height of the water, which is also, we could say, feet of head. That really matters in this calculation. There's a direct relationship between feet of head, which we measure in feet, and pressure, which we would measure in pounds per square inch, is a really common measurement for pressure. And this is also a conversion that's available on your formula sheet. So if we could write that as 1 foot of water is equal to a pressure of 0.433 psi. 1 pound per square inch is equal to 2.31 feet of water. So those conversions are really helpful when you're calculating pressure and doing those conversions. So calculating pressure, let's look at an example of that here. Your storage tank has 53 feet of water in it. What's the water pressure in pounds per square inch at the base of your tank? So we know that our storage tank has a height of 53 feet, right? And how would we calculate that pressure at the bottom? So we know that 1 pound per square inch is equal to 2.31 feet of water, and 1 foot of water equals 0.433 psi. Let's look at that here. So it's just a conversion, really. We're taking the height, so 53 feet, and then we're going to, on the left side of the equation, on the right side of the equation, we've got 0.433 psi over 1 foot. And this is our second conversion option, right? So we're going from foot of water here to psi to get the final pressure, because we just have ones on the bottom. And then we've got foot on the top, foot on the bottom. We can cancel that unit out, and that leaves us with a final answer of 23 psi. So 53 feet of water is equal to a pressure at the bottom of the tank of 23.
But he's doing nothing. He's nothing.
Okay, so if we're gonna let's go ahead and do a practice problem now. So this is give you a chance to practice this conversion. So we've got a storage tank on a hill, and it's 100 feet above a pump house. It has 345,000 gallons of water in it, and a water height of 34 feet. So go ahead and calculate the PSI, the pressure that is being measured in the pump house. So if we kind of visualize what this problem is asking here, this is kind of a photo that does that. So we've got our storage tank on the top of the hill, and that has a water height of 34 feet, right? So that's our storage tank. And then we have 100 feet of height between the water tank and the pump house. So that's going to be another 100 feet of water. And if we calculate those, we know that we have 134 feet of water in total for that. So knowing that, I'm going to give you all a chance to work on this. I'll give you 3 minutes to do that. We'll come back together and look at how we solve this problem. Okay. I'm gonna go ahead and close the poll here. If you have any answers, go ahead and get them in the next few seconds. Awesome, thank you. Great. Okay, go ahead and end the poll. And here's what we got. All right. So majority of you answered 58 PSI. That's great. Let's see how we did here. So for this, when we're calculating pressure in this practice problem, we're really just doing a conversion, right? So we're converting the height of water, feet of water, to pressure, right? So if we work through this, 58 is correct for this one. So let's go ahead and look at this question in detail. So our storage tank, right, we know is 100 feet above the pump house. It's got 345,000 gallons of water in it, and that water height is 34 feet. And this is like a little bit, sometimes you'll notice in these problems that you'll get a number like 345,000 gallons. That doesn't actually really mean anything. It's just kind of an extra detail. So you got to kind of take a look at the question, right, and kind of work backwards from there. So the question is, we want to calculate the pounds per square inch in the pump house. And all we need to do that is the water height, right? Because if we know the height of feet of water, then we'll be able to calculate the pressure. So we can kind of just ignore that gallons, that volume of water for this one. So all we got to do is set up our conversion. We've got our little grid here. So we've got, remember that because we're looking at the total height in the system above the pump house, we're adding the height of the water for the tank to the height that the tank is above the pump house, because that's going to give us our total height for that whole system since we're reading the pressure at the pump house. So we'll do 100 plus 34. That's going to give us a total height of 134 feet of water. And then we just have to convert that to pressure. So 134 feet over 1 on our left side of the equation. Since we want to end up with PSI, we got to have our PSI on the top and our feet on the bottom. We know that for 1 pound per square inch, it's 2.31 feet of water. Our feet get to cancel out because we've got one on the top, one on the bottom of our grid. Multiply across the top, 134 times 1 is going to give us 134. Divide that by 2.31 on the bottom times 1, and that is going to be 134 over 2.31, and that gives us a final answer of 134 feet in height is equal to 58 PSI for our final answer. So great job on that one. Just a little conversion practice at the end there. So that's really all I've got for today. I ended right on time. If anybody has any questions, I will stick around for a minute or two after this. Please feel free to stick around and ask questions if you have any about anything we covered today. Also, my email's on the screen here again. Please feel free to reach out to me. I'm always happy to talk and answer questions about webinars. And thanks to you all for attending this morning. Hope your day goes well. And also we'll hope to see you next time at the next webinar in the series. We've got drinking water regulations coming up on August 20th. And that's going to be our next one. That's 2 weeks from today. Hoping to see you there. And yeah, thanks everyone for attending and thanks for your participation today. It's a great webinar. Somebody is asking, let's see, Maria is asking, do you have more practice math problems? Yes, the answer is yes. We have a lot more practice problems. I don't have them kind of compiled in a sheet today, but we do have a bunch of practice problems that we use in our longer trainings that I'd be happy to send your way. So let me just make a note to do that. And I will be in touch with Andrew, who's kind of doing a lot of communications for this training, and have him send around those practice problems, because that's a really great question, because for so much of math, you just got to practice, and having those practice problems to work through is super helpful. So yeah, thanks. Thanks, everyone. Also, please feel free to reach out to me if you don't have a copy of that formula sheet that you'll need for the exam that you'll use on the exam. When you're working through those practice problems, super helpful to have the formula sheet. So I'd be happy to send that to you as well if you don't already have it. Awesome. Thanks, everybody. All right. I'm not seeing any more questions, so I think we'll go ahead and we can end the recording. And